Welcome back to the deep dive. Whether you're glued to sports stats, trying to make sense of the weather forecast, or wondering how that perfect movie recommendation popped up for you online, we're constantly interacting with numbers and data.
We really are.
But how do we move beyond just seeing a jumble of facts and figures to actually understanding what's going on?
That's the fundamental challenge, isn't it? Data is everywhere, but raw data alone. It rarely tells a story. It's the tools and techniques of statistics that allow us to, collect, organize, and interpret that data to reveal patterns and insights.
Absolutely. And in this deep dive, we're cracking open some foundational notes and documents you've shared. Our mission, to get a solid handle on the very first steps in that process, taking raw data and using descriptive statistics to make it understandable.
Sort of like learning the basic grammar.
Exactly. Think of it as learning the essential language to begin talking about data effectively.
We'll start with the big picture.
Wow.
What statistics fundamentally is and why it's become indispensable in almost every field imaginable.
Then we'll zoom in on the building blocks, understanding exactly what we mean by data and the different forms it can take, because, that dictates everything else you do, right?
It really does. And finally, we'll spend most of our time on the heart of descriptive statistics, the essential tabular and graphical tools, the tables, charts, and graphs that let us summarize, visualize, and start telling stories with those numbers.
Turning chaos into clarity.
That's the idea.
Okay, let's unpack this. So what exactly are we talking about when we say statistics?
The material we're looking at describes it as a process, really one that involves collection.
Gathering the info.
Right. Then analysis.
Making sense of it.
Presentation.
Showing it.
And interpretation.
Understanding what it means.
Yeah.
Collection, analysis, presentation, interpretation.
Exactly.
Okay, so if we were, say, studying the relationship between how much students study and their exam scores?
You'd first collect the data. That might mean surveying students about their study habits, getting their test scores, gathering those raw facts and figures.
Got it. Then analysis. This is where you clean up the data, maybe organize study hours into groups, or calculate averages for both study time and scores.
Right, applying methods to make sense of the collected data, crunching the numbers, basically, followed by presentation. How do you show your findings?
Tables, maybe, to organize things, or like a scatter plot graph to visualize study hours versus scores, see if there's a trend.
Precisely. You need effective ways to display it. And finally, interpretation. What did the results actually mean?
Does the graph suggest more study time generally leads to higher scores? Are there limitations, like maybe you only surveyed students from one specific class or didn't account for tutoring? What's the key takeaway?
Exactly. It's a systematic approach to answering questions using data. And a key point from the material is that this process isn't just for researchers and labs. Statistics is, it's woven into the fabric of modern life.
It really is. I mean, think about predicting weather patterns for farming.
Predicting rainfall.
Forecasting team performance in sports, or analyzing polling data to predict election results.
In business, too. Companies predict sales, calculate insurance premiums based on risk factors, or forecast economic indicators like inflation. It's constant.
And my personalized recommendations on Amazon or Netflix. That's statistics, isn't it? Analyzing my past behavior and comparing it to others.
Absolutely. Banks use statistical models to spot unusual patterns and detect fraud. That's a big one.
Right. And stores like Walmart and Amazon predict demand for specific products based on historical sales, seasonality, trends, all to manage their inventory effectively.
Pharmaceutical companies rely heavily on statistical analysis in clinical trials. Proving a drug's efficacy and safety before it reaches us. Think Pfizer, J&J.
It's crucial there. And online advertisers like Google or P&G use statistics to figure out which ads to show to whom for maximum impact.
Yeah.
It really is the engine powering countless decisions and systems around us.
Statistics branches out into areas like inference, risk and probability, correlation, modeling. It shows the breadth of the field. But our focus today is purely foundational, descriptive statistics. How do we take a set of data and simply summarize and present what's in that data?
Right, just describing what we have in front of us. The first step in describing data is understanding what data actually is.
Good point.
The material defines data as the facts and figures collected, analyzed, summarized for presentation and interpretation. And when you collect data for a specific study, that collection is called a data set. Makes sense.
It gives a helpful table example, maybe listing individuals, their ages, heights, weights, and genders. This helps clarify the building blocks.
Okay, so the elements are the individual things you're collecting data on in that table. Each person is an element.
Right. The people or the cars or the companies, whatever you're studying. And the variables are the characteristics of those elements that you're interested in measuring.
Age, height, weight, and gender in that example, the things you measure about the element.
Exactly. So an observation is the set of measurements you get for a single element. For one person, it would be their specific age, height, weight, and gender recorded together. One row in the table, typically.
Element, variable, observation. Got it.
Understanding these basic terms sets the stage. But the really crucial distinction, the one that kind of dictates everything else when you're looking at data, is whether it's categorical or quantitative.
This feels like a fundamental fork in the road for what you can do later. Categorical data is about putting things into distinct bins or labels, like gender, male, female, eye color, blue, brown, green, or maybe mobile phone brand, Apple, Samsung, Xiaomi.
Right. You can count how many fall into each category, but you can't really do arithmetic on the categories themselves. You can't average eye colors or add up phone brands meaningfully.
It's about classification.
Exactly. Quantitative data, on the other hand, consists of numerical values where arithmetic operations do make sense. Things like age, height, weight, income, test scores.
Numbers that mean numbers.
Pretty much. You can add ages, calculate average height, find the range of incomes. These numbers have mathematical meaning beyond just being labels.
Okay. And building on that, the material goes into the 4 scales of measurement, which give us even more granular detail about what kind of math is, well, allowed.
Yeah, think of these scales as levels of information embedded in your data. The most basic is the nominal scale. This is purely for naming or labeling categories.
Like the eye color, blood type, or country of origin examples. There's no inherent order. Blue isn't more than brown in any mathematical sense.
Exactly. You can only count frequencies within categories. That's about it.
Next level up is the ordinal scale. Now there's a rank or order, but the distance between the ranks isn't necessarily uniform or meaningful.
Right. Think movie ratings, 1 to 5 stars, or customer satisfaction surveys, like very dissatisfied, dissatisfied, neutral, satisfied, very satisfied. 5 stars is better than 4.
But the difference in goodness between 4 and 5 stars might not feel the same as the difference between 1 and 2 stars. The steps aren't necessarily equal.
Precisely. You know the order, but not the distance between points.
Then we have the interval scale. This has order, and now the intervals between values are equal and meaningful. But there's no true 0 point indicating the absence of the quantity.
Temperature in Celsius or Fahrenheit is the classic example here. The difference between 20 degrees and 30 degrees is the same 10-degree jump as between 30 degrees and 40 degrees. Equal intervals.
But 0 degrees Celsius doesn't mean no temperature or no heat. It's just a point on the scale. So you can't say 40 degrees C is twice as hot as 20 degrees C in a meaningful ratio sense.
Exactly. IQ scores and calendar years work like this too. You can add and subtract differences, but ratios don't make sense.
And the strongest, the top level, is the ratio scale. This has everything the interval scale has: order, equal intervals, but it also has a true 0 point, a meaningful 0.
Like height, weight, time, income, or temperature in Kelvin. 0 height means no height. $0 income means no income. 0 kilograms means no weight.
And with that true 0, ratios are meaningful. 4 kilograms really is twice as heavy as 2 kilograms. You can say someone earning $100,000 makes twice as much as someone earning $50,000.
Right. And the key insight here, as the material points out, is that the scale of measurement isn't just academic trivia. It fundamentally dictates which statistical methods and visualizations are appropriate.
You can't calculate an average blood type because that's nominal data. It wouldn't mean anything.
But you can calculate an average height because that's ratio data. Understanding the scale prevents you from, using tools that just aren't suited for your data type, which can lead to really weird or wrong conclusions.
Makes sense. Also briefly touches on other ways to classify data, like time series versus cross-sectional.
Yeah, time series data is collected over time, like tracking the price of a specific car model year after year. Cross-sectional data is collected at a single point in time, like looking at the prices of all the different used cars sold on one particular day.
Okay. And discrete versus continuous data.
Discrete data usually comes from counting how many cars were sold. It has to be a whole number, 0, 1, 2, etc. You can't sell 2.5 cars. Continuous data typically comes from measuring how much did the car cost or what was its weight. It can, in theory, take on any value within a given range. Price could be $10,500.50. Weight could be 1,500.75 kilograms.
Got it. Counting versus measuring, essentially.
That's a good way to think about it.
And before we fully dive into describing the data we have, quickly mentions the idea of how we study data, touching on experimental versus observational studies.
Right. An experimental study is where you, the researcher, actively control variables to see the effect of one on another, like testing a new marketing campaign on one group of customers while keeping the old campaign for another group and comparing sales. You intervene.
Whereas an observational study just collects data on what's happening naturally without intervening, like surveying shoppers about their habits without trying to influence what they buy.
Exactly. You just watch and record. And then there's the crucial distinction between a population and a sample.
The population is the entire group you're interested in making conclusions about, like all potential voters in an election or all cars of a certain model.
And a sample is the smaller subset of that population you actually collect data from, because studying the whole population is often impractical or impossible.
So you study the sample to learn about the population.
Precisely. This is key when you want to use information from a sample to make statements or inferences about the whole population. That's the realm of statistical inference.
Testing a new car lubricant on a sample of maybe 100 cars.
To infer its likely effect on fuel efficiency for all cars of that model. While statistical inference is a huge and vital field, for today, our focus is simpler. Using descriptive statistics to summarize and present the data we have, whether that's from the whole population or just our sample, just describing what we see.
All right, let's get to the good stuff then, descriptive statistics in action. How do we take that raw data pile and make it make sense? You said the methods change depending on whether the data is categorical or quantitative.
That's right. Let's start with categorical data, those labels or groups like phone brands or eye colors. A fundamental tool here is the frequency distribution.
Which is basically just a table.
Exactly. A simple table that lists each category and how many times it appears in your data. So if you surveyed 20 people about their phones and found 8 use Apple, 7 use Samsung, and 5 use Xiaomi, that listing is your frequency distribution.
Simple count. Easy enough.
From that, you can easily calculate the relative frequency, which is just the proportion for each category. So for Apple, it's 8 out of 20, or 0.4.
And the percent frequency is just that proportion times 100, so 40% for Apple. It shows the share of the total for each category.
Right. Frequency, relative frequency, percent frequency, they all tell slightly different versions of the same story. And to visualize this categorical data...
Bar charts and pie charts, usually.
Those are the main ones, yes. The bar chart uses the height or length of bars to show the frequency or percentage for each category. The categories are distinct, so the bars typically don't touch.
And the pie chart uses slices of a circle to show the percentage each category represents of the whole. Good for seeing proportions.
Exactly. The material also briefly mentions the Pareto diagram, which is a specific type of bar chart often used in quality control, where the bars are ordered from highest frequency to lowest, helping to identify the most common issues.
Okay, that covers categorical. Now, for quantitative data, those meaningful numbers like, say, project completion times in days. If you have lots of different completion times, just listing every single one in a frequency table isn't very helpful, right? It'd be too long.
Correct. So for quantitative data, we often group the values into classes or ranges. The material gives an example using project completion times. Instead of listing every specific number of days, like 12, 15, 17, 18, 21, you might group times into classes like 10, 14 days, 15, 19 days, 20, 24 days, and so on.
And then you count how many projects fell into each time range.
Precisely. That gives you a frequency distribution table with classes. The material points out some important things to consider when you're creating these classes.
Like choosing the right number of classes. Not too few, not too many.
Right. And determining a sensible class with how wide each range is. Making sure the class limits are distinct so each data point falls into only one class. You don't want overlaps like 10, 15, and 15, 20. It should be like 10, 14, 15, 19.
And calculating the class midpoint, which is just the middle value of each class range, useful for some calculations later.
Exactly. These choices affect how the final summary looks. Now, the primary graph for showing the distribution of quantitative data using these classes is the histogram.
Okay, so the variable, like completion time, goes on the horizontal axis, and the frequency or percentage goes on the vertical axis, like a bar chart. But you said there's a key difference.
Yes, and this often trips people up. The bars in a histogram touch each other.
They touch. Why?
It's not just a style choice. It's because the classes represent continuous ranges of a numerical variable. The 10-14-day range flows right into the 15-19-day range. The touching bars visually represent this continuity. Bar charts have gaps because the categories, like phone brands, are distinct and separate.
Ah, Okay, continuous ranges mean touching bars. Discrete categories mean separated bars. That makes sense.
And the shape of that histogram is incredibly informative. It immediately gives you a visual sense of how the data is distributed. Is it piled up in the middle, skewed to one side?
A histogram that's moderately skewed left. That means most of the values are higher, clustered on the right, but there's a tail stretching out to the left from a few low outliers.
Exactly. Maybe scores on an easy exam where most people did well, but a few scored poorly, pulling the average down slightly. Or the age distribution in a retirement community, lots of older folks, fewer younger ones.
And highly skewed left would just be a more extreme version of that.
Right. Conversely, moderately skewed right means most values are lower, clustered on the left, with a few high outliers pulling the tail out to the right.
Like income distribution in most companies, where most employees earn around a certain level, but a few executives earn much, much more.
That's a classic example. And highly skewed right might be something like the ages of tech startup founders, maybe many are relatively young, with just a few older outliers.
And then there's symmetric, often looking like a bell curve. This tells you most values cluster around the middle, and it tapers off pretty evenly on both sides.
Like the heights of adult women in a large population, perhaps. Just looking at the histogram shape gives you immediate insight into the data's central tendency and spread, even before you calculate specific numbers.
It's a powerful visual summary. Ogive. O-G-I-V-E.
Yes, the ogive. It's a graph that shows cumulative frequency or cumulative percent frequency. Essentially, it plots points representing how many data points are below a certain value. The upper limit of each class is plotted against the total count up to that point. It creates an S-shaped curve.
So it shows accumulation.
Okay.
Now, what about looking at relationships between two variables together in a table?
That's where cross-tabulation, or contingency tables, come in. It's basically a table that summarizes data for two, or sometimes more, variables simultaneously. You see how the categories of one variable line up with the categories of another.
Maybe looking at something like student performance, like high, medium, low marks, cross-tabulated by the number of days they took to complete a project, like categorized into few, moderate, many days.
Exactly. It allows you to see the joint distribution. Are students who take longer also getting lower marks, for example? You can look for patterns between the variables.
But this leads us to something really interesting and kind of tricky. Simpson's paradox.
Ah, yes. This is truly fascinating and a critical lesson in data analysis. It can be quite counterintuitive.
As a phenomenon where a trend or comparison that holds true within several different groups of data actually disappears or even reverses when you combine those groups and look at the overall picture.
It uses a really good example about application selection rates, comparing male and female applicants across two different departments. Let's call them A and B.
Right. So if you just look at the overall numbers, maybe out of 1,000 male applicants and 1,000 female applicants total, the data showed 260 women were selected. That's 26%. And 376 men were selected. That's 38%.
Okay, so looking only at that overall summary, it seems like men have significantly higher selection rate, 38% versus 26%.
Yeah, you might look at that aggregate number and think there's some kind of overall bias favoring men in the selection process.
But then the paradox emerges when you break it down and look within each department separately. In Department A, the numbers were something like 80 women selected out of 100 applicants.
There's like 80% selection rates for women in Dep Day,
Compared to 368 men selected out of 800 applicants in that same department.
which is 46% for men in Dep Day.
So wait, in Department A, women actually had a much higher selection rate, 80% than men, 46%.
Exactly. Now look at Department B. There are 180 women were selected out of 200 applicants. 90% selection rate for women in Dep B. Very high.
Compared to only 8 men selected out of 200 applicants.
That's only a 4% selection rate for men in Dep B. So in Department B2, women had a vastly higher selection rate than men.
This is Simpson's paradox in action. In both individual departments, women were selected at a significantly higher rate than men. Yet when you combine the data, it looks like men had the overall advantage.
How does that happen? Is it because the application patterns were different?
That's the key, as the material implies. It likely happened because, say, maybe Department A was much harder to get into overall, lower selection rates for both genders, but still higher for women within it, and far more men applied there. And maybe Department B was easier to get into, higher selection rates for both, especially women, and proportionally more women applied there.
So the overall average gets skewed by where people applied. The large number of men applying to the tougher Department A drags down the overall male average, even though men did worse than women within that department. And the large number of women applying to the easier Department B doesn't lift the overall female average enough to overcome the Department A effect in the combined total.
Precisely. It's a powerful example showing that simply aggregating data, just combining groups, can be incredibly misleading. It can hide or even reverse the underlying trends present in the subgroups.
Wow, so the context, like which group applied to which department, in what numbers, or whatever the lurking variable is absolutely essential to understand the real story. You can't always trust the overall summary statistic.
Absolutely not. It's a crucial reminder to always ask, is this combined data hiding different stories within subgroups? You need to dig deeper sometimes.
Okay, that's a really important takeaway. Visualizing the relationship between two quantitative variables, not categories, but two sets of numbers.
Right. The main tool for this is the scatter diagram, or scatter plot. You plot points on a graph where each point represents a pair of values for one element.
Like plotting each student's hours studied on the horizontal axis against their exam score on the vertical axis. Each student is one dot on the graph.
Exactly. And just by looking at the pattern of dots, you can often get a sense of the relationship. Do the points seem to trend upwards together, downwards, or is it just a random cloud?
And you could often add a trend line to that scatter diagram.
Yes, a trend line is a line drawn through the points that tries to approximate the general relationship. It helps visualize the direction and maybe the strength of the association.
Showing if the variables tend to increase together, a positive relationship, or if one tends to decrease as the other increases, a negative relationship, or if there's really no clear linear pattern.
That's the idea. It's a first look at potential correlation between two numerical variables.
Laying out which types of tables and graphs are best suited for categorical data versus quantitative data.
Yes, it recaps things like frequency distributions, bar charts, pie charts for categorical, and frequency distributions with classes, histograms, ogives, scatter plots for quantitative. Nice little cheat sheet.
It is. Wow, okay, that was definitely a deep dive into the basics. We started by seeing how statistics is really that essential process for making sense of the data deluge all around us.
Collection, analysis, presentation, interpretation.
Yeah.
Then we explored the fundamental structure of data itself, elements, variables, observations, and got into that crucial distinction between categorical and quantitative data types.
And why those four scales of measurement, nominal, ordinal, interval, ratio, really matter for choosing the right statistical tools later on.
We briefly touched on study types and the idea of sampling before focusing entirely on descriptive statistics.
Right. Learning how things like frequency distributions, bar charts, pie charts for categories,
and histograms, ogives, and scatter plots for quantitative data allow us to effectively summarize and visualize what we have, giving us quick insights into distributions and relationships.
And we definitely wrestled with that intriguing puzzle of Simpson's paradox, seeing how simply combining data can sometimes completely reverse the truths found within the subgroups. A real cautionary tale.
It really is. These concepts, they might seem basic, but they are absolutely the bedrock. They're how we begin to translate the raw, often messy language of numbers into understandable summaries and visuals.
Whether you're looking at business reports, scientific findings, news articles, or just trying to figure out why Netflix recommended that movie.
Exactly. It's about starting to speak the language of data.
So thinking about all this, now that you've seen the power of these basic tools and understood how the type of data dictates the tool, and how even the way you group or combine data can completely change the story, like we saw with Simpson's paradox, how might you look at the next graph or statistic you encounter differently?
Maybe pause and ask, what kind of data is this? Really, what scale is it measured on? Am I seeing the whole picture, or could there be different stories hidden within subgroups if I looked closer?
Food for thought indeed. Thinking beyond the surface level. Thanks for joining us on this deep dive.